Assalamu alaikum, everyone. All right, so let's get started. Let me just turn the pen on. Okay. So in the last lecture, we did the fundamental theorem of calculus, part one, which connected basically definite integrals to derivatives, right? So this was a statement which said that if small f is a continuous function, right, and you define capital F as this function here, capital F of x is the integral from some constant to x of f of t dt. Then the derivative of capital F with respect to x is just small f of x. So basically, definite integration and differentiation reverse one another, right? So let's do some examples of applying the fundamental theorem part one. Just scroll down here. So if I want to differentiate this function is the integral from 1 to x squared of cos t dt. So you see how this is a function of x, right? It's a function of x. If I integrate cos t with respect to t and apply the limits of integration 1 to x squared, this would give me a function of x squared, of x basically. Now, if I want to differentiate dy by dx, what do you think I should get? Remember that the fundamental theorem says, let me just rewrite it here, that if you have d by dx of integral from some constant to x of f of t dt, then this is just f of x, right? So should dy by, so what's small f here? Let me just erase this. What is small f in this question? Small f is the cos function, right? So should I just write that dy by dx is cos of x squared? Is that enough? Is that the correct answer? So this just says that the derivative of such an integral would be just small f at x. Now, since I have x squared here, should I just write cos of x squared? The fundamental theorem requires you to have just x here, not a function of x, right? Your upper limit should be just x, not a function of x. Here, our upper limit is further a function of x, right? So it's almost like writing integral from a to some g of x, d by dx of that, and then f of t dt, right? So we're not differentiating with respect to g, we're differentiating with respect to x. And our upper limit is a function of x. So what do we need to apply here? I want to differentiate with respect to x, but I have it's like a function of x, right? So I need to apply the chain rule here because my upper limit of integration is not just x, it's a function of x. So it's almost like a composition, right? This entire thing is a function of x squared, and x squared is a function of x. So I need to apply the chain rule. And how do I do that? Well, let me just write u is equal to x squared just to make it very clear. If I let u to be equal to x squared, then now this integral becomes the integral from 1 to u of cos t dt. And so I want dy by dx, right? The fundamental theorem of calculus, if I apply it directly, will give me dy by du, and then I can calculate du by dx. This is how I would apply the chain rule. Dy by dx will be dy by du times du by dx, where u is x squared. So I know that du by dx is 2x, right? So dy by du is simply cos u by the fundamental theorem of calculus, part one, and du by dx, we just had to differentiate x squared. So our final answer is not just cos of x squared, it's 2x cos of x squared. Right? So it's important to remember that if the upper limit of integration is not just x, it's a function of x, then you have to apply the chain rule. You cannot simply write, in this case, you cannot simply write cos of x squared. That would be incorrect. Yes, Amna?
Ma'am, why dy by du cos u? I don't understand that.
Because of the fundamental theorem of calculus. So just look at this, right? And so dy by du is basically d by du of the integral from 1 to u cos t dt, right? And so we're differentiating with respect to u. Our upper limit is also u, lower limit is a constant, so we can apply the fundamental theorem part 1 directly. So this is cos of u. Is that clear?
Yes.
So I'll just write the fundamental theorem again, right? It says d by dx of integral from a to x of f of t dt is just f of x. It's f at the upper limit of integration, which is x. Now, instead of x, we have u here, right? So our upper limit is u, and we want to differentiate this with respect to u. Is that clear?
Yes, ma'am. Yes.
The reason we can't do that directly here is because we don't just have x here. We have x squared, and I want to differentiate with respect to x. So I have to further differentiate x squared. Right? Here we just have the u here is just an intermediate variable that I've created just to help you see the chain rule. But if that's confusing, just know that in order to differentiate y with respect to x, I'm first differentiating y with respect to x squared, right? And when I do that, I get cos of x squared, but then I have to further differentiate x squared, which is 2x. So if u is confusing you, you can think of it like that. First differentiate this with respect to x squared, which is the upper limit, and then further differentiate x squared with respect to x. All right. So notice how the lower limit, which is a constant, doesn't matter, right? Even in the statement for the fundamental theorem of calculus, it didn't matter. And obviously, so when we apply it, this could have been, 2, 3, 10, anything, it wouldn't matter because it's a constant limit of integration, right? So the fundamental theorem says that if this is a function of x and you want to differentiate it, the lower limit doesn't play any role. All right, so now let's take a look at this next example. If I want to differentiate this, again, keeping in mind the statement of the fundamental theorem, it said that if you want to differentiate integral from a to x f of t dt, then that's equal to f of x. So in order to apply the fundamental theorem here, we have to rewrite this in the form that we see in the fundamental theorem. So what's the problem here? The problem here is that your lower limit is a function of x and your upper limit is a constant. The fundamental theorem requires your lower limit to be a constant, and then the upper limit should be x, or if it is a function of x, then we have to further apply the chain rule. So how do we flip these limits of integration? By using the property of definite integrals, which is that if your limits of integration are flipped, then you have an extra negative sign outside, right? So integral from a to b of f of t dt is equal to negative integral from b to a of f of t dt. So by doing that, I'm now making sure that the lower limit is a constant and the upper limit is a function of x. Now, what do I do after this? How do I apply the fundamental theorem? Again, just like above, I apply the chain rule, right? So this would be negative sine of x squared times the derivative of x squared, which is 2x. Any questions? All right. What do I do here now? Let's look at this last example. I have the integral of the function t squared from sine x to cos x, and I want to differentiate it. Now again, because it's the derivative of an integral, I know I should be applying the fundamental theorem, but I need to bring this integral in a form such that the lower limit is a constant and the upper limit is either x or some function of x. Here, both lower and upper limits are functions of x. So what can I do? Remember the property of definite integrals, that if you have an integral from a to b of f of t dt, then that's equal to the integral from a to c f of t dt plus c to b f of t dt. So I can just choose any constant. Remember, the constant limit doesn't play a role in my final answer. So I can just choose any c and write this integral here as the sum of these two integrals. So integral from sine to c plus the integral from c to cos. Right? So now, and again, I still want to differentiate this. Now, this integral here, the one from c to cos, is in the form where I can apply the fundamental theorem. For this one, I need to do one more thing. I need to flip the limits of integration so that the constant becomes a lower limit and sine x becomes the upper limit. So I get this in the end, right? I need to now differentiate negative integral from c to sine x of t squared dt plus integral from c to cos x of t squared dt. And now I can again complete using a combination of the chain rule and the fundamental theorem. So I can do these separately. Any questions? All right. All right, so if there are no questions, I'll stop sharing here and share the next lecture set. All right, so the previous theorem that we did was the fundamental theorem of calculus part 1. And so obviously there's a part 2 as well. Part 2 will help us evaluate definite integrals much more easily. So before this, whenever we were trying to evaluate definite integrals, we would go to Riemann sums. Using the fundamental theorem of calculus part 2, we are now going to establish a connection between definite integration and indefinite integration. All right. So again, if small f is a function that is continuous on this interval a to b, and capital F is any antiderivative of small f. Now again, by antiderivative, I mean the indefinite integral, right? So in other words, f prime of x is f of x, right? So f is such a function such that the derivative of f, the derivative of capital F is small f, right? Or capital F is the antiderivative of small f. So if that's the case, then we can write that the integral of small f from a to b is capital F at b minus capital F at a. So f is basically the definite integral. Sorry, let me repeat that. F is the indefinite integral. F is the indefinite integral or antiderivative of small f, right? So we're basically saying that if I want to integrate small f from a to b, all I need to do is evaluate the indefinite integral, which is easier for me to do because indefinite integral is just the reverse of differentiation. And then evaluate that at the upper limit of integration, which is b, minus the same function at the lower limit of integration. Right, so this is so here I have the definite integral, and here I have the indefinite integral. And so you see how they're both connected. Before this, if you wanted to evaluate this, you would use Riemann sums. Now, if you want to evaluate it, as long as you know an antiderivative of small f, or basically the indefinite integral of small f, meaning integral of f of x dx is capital F of x plus any constant c, then you can evaluate the definite integral of small f as well from a to b, which is capital F at b minus capital F at a. Does everyone understand this statement before we move on to the proof?
Ma'am, can you please go over it just one more time?
Okay. So if I have this function small f of x dx, right? And I have the indefinite integral. And I'm saying that the indefinite integral is capital F of x. You can have a plus c or anything. It's just one of, remember that indefinite integral gives you a family of functions. And they're basically the antiderivatives of your original function. So capital F of x is any antiderivative of small f of x. Right? And this is based on that indefinite integration concept where we are reversing differentiation. Now I'm saying that if you want the integral of the same function, small f of x, but now it's a definite integral from a to b, which was, remember, this was the Riemann sum idea. We're saying this is the same as evaluating capital F at b minus capital F at a, where capital F was just the indefinite integral. So now in order to do definite integration, rather than going to Riemann sums, you can simply do indefinite integration, which is just the reverse of differentiation, right? And then evaluate that at the limits of integration and then subtract. Right? If you want to write it another way, you can write it as this, that the definite integral of the derivative of a function is just that same function evaluated at the limits, meaning capital F at b, capital F at a, and then subtract. Right? So the relationship between small f and capital F is, you can write small f of x as either the derivative of capital F of x, or you can write the integral of small f of x is capital F of x. Right? So this is the relationship between small f and capital F. Is that clear?
Yes, ma'am.
Okay. So to prove this, we start with trying to define a function whose derivative is small f, or a function that is the antiderivative of small f, right? So one function that we know from the previous fundamental theorem is that this capital G of x, which I define as the integral from a to x f of t dt, this capital G is an antiderivative of f. Why? Because the derivative of G is f. So G is the antiderivative of f, meaning the integral of f is G. I know that if this is confusing, just write it out like this. If G prime of x is f of x, then G of x is the integral of f of x, G of x plus any constant c. Right? So G is the antiderivative of f. Right? So now again, the integral or the indefinite integral of small f can be written as G of x plus c. So any antiderivative of small f can be written as G of x plus any constant c. Right? G is one such function, but g plus any constant will also be an antiderivative. So that means that whatever this f is in our statement here, this capital F, will be g of x plus some constant c, because both of them are antiderivatives of small f. So they will only differ by a constant. Now, if capital F of x is g of x plus c, then what does f of b minus f of a look like? F of b minus f of a is g of b plus c minus g of a plus c. So the c and c will get cancelled. It becomes g of b minus g of a. What is g of b by definition? Just plug in b instead of x here. So that's the integral from a to b of f of t dt. And what is g of a? Again, plug in a instead of x in the expression for g here. So that's the integral from a to a of f of t dt. And this is 0 by definition. We're integrating a function from a to a. So this is 0 by definition. So we're just left with the integral from a to b of f of t dt. And that's exactly what we wanted to prove, right? We wanted to prove that the integral from a to b of f of t dt is just capital F of b minus capital F of a. Yes, Amna?
Ma'am, why is the g of a equal to the integral of a from a?
Just plug in a here instead of x.
Oh, okay.
Right?
Okay.
This is g of x. Right, so any questions about the proof? All right, so again, the importance of this part of the fundamental theorem of calculus is that it makes definite integration easier. You don't have to go to Riemann sums. You can use everything that you've learned for indefinite integration and apply that. All you need to know in order to evaluate this definite integral is to know the indefinite integral of small f. And then it's just a matter of evaluating that function and subtracting f of b minus f of a. All right, so the main technique that, one of the more important techniques that we studied for indefinite integrals was the U substitution technique. So that's also applicable now to definite integrals. The only extra step that we have to be very careful about is that now we also have these limits of integration that we have to be careful about. So remember that if I have the integral of f of gx, g prime x dx, then if I use the substitution u is equal to g of x, this becomes integral of f of u du, right? Because this here becomes du. And then hopefully this is an easier integral to evaluate. And so we're able to evaluate this, whatever it's equal to depending on f. Now, the extra thing here in a definite integral is that we have these limits of integration. And these limits of integration are basically values of x, right? This is integral of this function with respect to x from x is equal to a to x is equal to b. Now, when I do my substitution, I end up with integral of f of u du. And so I cannot apply x is equal to a and x is equal to b. This a and b correspond to values of x, not of u. So I need to adjust these as well. This is that extra step that I need to do for substitution in definite integrals. So how do I find the corresponding values of u? Well, I have an equation. I have a formula connecting u and x, which is my substitution, right? U was g of x. And so plug in x is equal to a and x is equal to b. That'll give you the corresponding values for u, g of a and g of b. So when I do my substitution, in order to complete my substitution, I also have to change these limits of integration. When x is equal to a, u is equal to g of a, and when x is equal to b, u is equal to g of b. So these are my limits of integration for u. And now I can integrate, because now everything is in terms of u. All right, so let's do an example. So if I have this integral of 3x squared times square root of x cubed plus 1 dx from -1 to 1. Now remember, this is x is equal to -1 to x is equal to 1. So if I let u be equal to x cubed plus 1, then du is 3x squared dx. And we already have 3x squared dx here, right? So this, inside the integral, it'll become square root of u du. But I also have to change the limits of integration. So when x is equal to 1, u will be equal to, remember, u is x cubed plus 1, so u will be equal to 1 cubed plus 1, which is 2. And when x is equal to -1, u will be equal to -1 cubed plus 1, which is 0. So my integral becomes integral of square root of u du from 0 to 2. So everything has changed in terms of u. This here became du, this became square root of u, this became -1 became 0, and 1 became 2. And now, since everything is in terms of u, now you can integrate. Now, how do I integrate here? What's the integral of square root of u du? U raised to power 3 over 2 over 3 over 2, right? That's the indefinite integral. All I need to do is evaluate this at 2 and evaluate it at 0 and then subtract using the fundamental theorem part 2, right? So I just need to evaluate. So first I'm going to integrate square root of u. That's going to give me u raised to power 3 over 2 over 3 over 2. Right? And then this bar means that I still have to evaluate it at 0 and at 2 and then subtract. So I evaluate this at 2, which is 2 times 2 raised to power 3 over 2 over 3. And then I evaluate it at 0, which is just 0. And then I subtract the 2. And so my final answer is 4 times square root of 2 over 3. How did 3x squared become du? Because u is x cubed plus 1. Right? So du is 3x squared dx. Just differentiate x cubed plus 1. You get 3x squared. Is everyone clear on how we applied the limits of integration here? We first do the integration, and then always remember, it's common for students to just do the integration and forget that you have these limits that you need to apply. So this bar will always remind you that you need to still apply these limits of integration to get the final answer. And since everything is in terms of u, you can simply apply these, you can use 0 and 2 as direct inputs to this expression and then subtract. Any questions? All right. So now let's do one quick result on what we call odd functions. So odd functions by definition are functions that satisfy this for all x. F of negative x should be negative f of x. So if this is some value of x and this is my function value f of x, then f of negative x is just negative f of x. So the function value corresponding to negative x is the negative of this value here. So just a reflection here. So this will be f of negative x. This point here corresponds to the point on the graph corresponding to negative x. And this should be true for all x. So if I think about this in terms of symmetry, the graph of my function should be symmetric about the origin, meaning that if, for example, if this is a point on the graph, then if I draw a line connecting this point and the origin, then the same distance here on the other side will give me another point on the graph. So the origin serves as a mirror to the graph, right? So again, if this pink point here is a point on my graph, its reflection in the origin will also be a point on the graph. And if this corresponds to x, then this will correspond to negative x. And since this is f of x, this will be negative f of x. And this is, of course, this is only true for odd functions. It's not true for all functions. If a function satisfies this, then it is, by definition, an odd function. So some examples are sine x, right? So this is the graph of sine x. You can see how it's symmetric about the origin, right? Any point, if you take any point on the graph, its image in the origin is also lying on the graph, right? Similarly, x cubed is also symmetric about the origin, and it's also an odd function, right? So what do you think if I have, for example, if I have sine x dx from minus pi to pi, meaning basically I want to integrate from minus pi to pi. Without actually doing the integration, what do you think the answer is? Knowing what definite integration is, remember it's net area, right? What do you think the answer is? The answer is 0, because this blue shaded area is exactly going to be equal to this yellow shaded area. The yellow shaded area will count as negative, the blue one will count as positive. When you add them together, you'll get 0. So this is to say, this is just a specific example, but in general, the definite integral of an odd function over a symmetric interval. What do I mean by a symmetric interval? An interval that is symmetric about the origin. So minus a to a, where a is any real number, right? So the definite integral of an odd function over a symmetric interval is always 0. So if f is an odd function, then f of x from any minus a to a will be 0. So if you see such a function, you don't have to go into the details of actually getting the integral. You can directly say that this will be equal to 0. Because the area on the left, well, the area on the left and the right will cancel each other out. The left and the right of the origin. All right. So we can actually prove this based on the definition of an odd function. Now, the integral from minus a to a of f of x dx, I can break it into two integrals, from minus a to 0 and from 0 to a, right? Now, f of x is always equal to, remember the definition of an odd function is that f of negative x is negative f of x, right? So that means that just multiply both sides by -1. That gives you f of x is negative f of negative x, right? I just multiplied both sides with -1. So this f of x here, I can write it as negative f of negative x, right? Now I can do a substitution, which is u is equal to negative x. So du is negative dx. And my limits of integration, when x is negative a, u becomes a. And when x is 0, u becomes 0. So this integral here, let me just change the color. This integral here becomes integral from a to 0 of f of u du. Right? And this one I've left untouched. This one on the right is untouched. Now, if I swap the limits of integration, what do I get? I get negative integral from 0 to a of f of u du. Now, this integral here, let me just clear this. This integral here and this integral here are basically one and the same thing. Even though you have a u here and you have an x here, remember, this is just a variable. It's just a placeholder, right? The function is the same. The limits of integration are the same, right? So both of these integrals are exactly the same. With one, you have a negative sign. With the other, you have a positive sign. You're adding them together. The answer should be 0. Right? And the main thing that we used here was the definition of an odd function. Any questions? Okay. All right. So let's move on to logs and exponentials. And I think this will be the last topic. We're just going to introduce the definition and do the differentiation and integration of these functions. All right. So the natural log function is defined as such. It is defined as the integral of 1 over t from 1 to x, where x is a positive number. This is how natural log is defined. Now, before we go into this definition, if I just ask you the integral of 1 over t dt, right? What is that equal to? Using what we know so far, if I try to, so this is the integral of t raised to power negative 1 dt. And if I try to apply the power rule, I get t raised to power negative 1 plus 1 over negative 1 plus 1 plus c. And that gives me division by 0. So this is an incorrect application of the power rule because the power rule does not apply to this one case where my exponent is negative 1. When you have the integral of 1 over t dt, so far, based on what we know, we cannot evaluate it unless we define the natural log. Right? So the power rule does not help you with this integral. It helps you when you have t raised to power any other number, but not when you have t raised to power negative 1. All right? In order to evaluate this integral, we have this expression, this function called the natural log. So the natural log of x is defined as the definite integral from 1 to x of 1 over t dt. Now, 1 over t, the graph of 1 over t is this. And since we're only concerned with x being positive, right? So we're just concerned with this part of the graph here, right? Just this part of the graph here. So that's what I've drawn here. So you have this graph and you want you want the integral of the function from 1 to x. So this is 1 and obviously 1 over 1 is also 1. So if x is greater than 1, then it's basically this area here. That integral or the natural log of x is this shaded area here, whatever the value of this shaded area is. And so if x is greater than 1, natural log of x gives us the area under the curve from 1 to x, and that's a positive area, right? So natural log of x is positive when x is greater than 1. What about when x is equal to 1? Then the natural log of x is just the integral of 1 over t from 1 to 1, which is 0. So the natural log of 1 is equal to 0. And what if x is less than 1? If, well, it's still positive, but what if x is less than 1? What if x is some number here? Then it's this shaded area, right? But now going from 1 to x in this direction. So is that, will natural log of x, when x is less than 1, will that be positive or negative? Looking at this shaded area here, where we are now integrating from 1 to x, so in the reverse direction. Will natural log of x in this case be positive or negative? Negative, correct. Because remember, we're integrating from 1 to a number smaller than 1, and the resulting area is above the x-axis. So this area itself is positive, but because we're going in the opposite direction, it becomes negative. Right? This is using the fact that the integral from 1 to x will be equal to the negative of the integral of from x to 1. All right, so the natural log, basically, the graph of the natural log looks something like this, and it corresponds to that graph that we have above. So when x is equal to 1, the natural log of x is simply 1. When x is greater than 1, the natural log is positive. When x is less than 1, and still x still has to be positive, right? That's the domain of my function. So when x is less than 1, my natural log is negative. Now, it's an increasing function. Why? Because as x increases, the area under my curve increases. Right? The area under this curve, 1 over x, increases as x increases. But because as x gets very, very large, this graph becomes very, very close to the x-axis, the rate of increase decreases, right? So after a certain point, well, not, let me just, for example, if this is x and then I add x plus delta x, this change in area keeps becoming smaller and smaller as x becomes larger, because my graph gets closer and closer to the x-axis. So the additional area that you're adding as x gets larger becomes smaller. So this increase in the graph, or the slope of the tangent line, becomes smaller and smaller because the extra area that you're adding is becoming smaller and smaller. So the graph, or ln x, flattens out. Not completely, but you can see that the slope of ln x becomes smaller or less steep as x increases. And what's happening as x gets closer and closer to 0? So if x is less than 1 and it's getting closer and closer to 0, your area is becoming larger and larger. So if as x becomes very, very close to 0, ln x becomes larger and larger and negative. So as x approaches 0 from the right-hand side, ln x approaches negative infinity. Any questions? Does everyone understand the dynamics of this graph? Okay. So again, the domain of the natural log is all positive real numbers. The range is all real numbers, right? So natural log can take all real values. All right. So the derivative of the natural log of x is the derivative of this integral, right? The derivative of the integral from 1 to x of 1 over t dt. where x is positive. So using the fundamental theorem of calculus part 1, that is just 1 over x. Right? That's the this inner function here at x. So that's just 1 over x. So the derivative of the natural log of x is 1 over x. And so correspondingly, the integral of 1 over x dx is natural log of x plus c. And for now, this is only when x is greater than 0. So we have the integral of 1 over x dx, but for now, that's only when x is positive. In a moment, I'm going to also evaluate this for when x is negative. But when x is positive, I write this as ln x plus c. Because remember, ln is, we can also call this ln or ln or natural log. Natural log is only defined when x is positive, right? So for now, the integral of 1 over x dx is ln x plus c only when x is greater than 0. We'll deal with what happens when x is less than 0 in a moment. And so now that you know the derivative of the natural log of x, you can now use all of the other properties of and methods of differentiation that you've done in combination with the natural log. So for example, the derivative of ln of x squared plus x plus 1 will be what? This is now, just like any other function, this is a composition of the natural log and x squared plus x plus 1. So you have to apply the chain rule. So first you differentiate the outer function, which is the natural log, with respect to the inner function. So the derivative of the natural log is 1 over the input. So I get 1 over x squared plus x plus 1. And now I have to differentiate the inner function. So that's 2x plus 1. So my final answer is 2x plus 1 over x squared plus x plus 1. Any questions? Yes, here, so x squared plus x plus 1 should be positive. Right? Now, let's do some properties of natural log. So the first property, so natural log is actually very useful in the sense that it simplifies, it makes products and powers and quotients a bit easier, or it simplifies them. So the first is involving a product of two numbers. So if you have, again, assuming a and x are both positive, if you have the natural log of a times x, then that's just equal to the sum of natural log of a and natural log of x. So ln of ax is just ln of a plus ln of x. So the natural log converts a product into a sum. Now to prove this, if you notice, the derivative of natural log of ax is what? It's 1 over ax times a, using the chain rule. So that's 1 over x. We also know that the derivative of ln of x is 1 over x as well. So the derivative of ln ax is 1 over x, the derivative of ln x is 1 over x. So they both must differ only by a constant. They both have the same derivative throughout, right? So they both must differ only by a constant. Ln x minus ln ax should just be a constant. Now, how do I find this value of c? I can find this, and this is true for all x, right? So, or for all values of x and even for a, right? So if I can plug in some value of x here, I can find a corresponding value of c. Since this is true for all x, I can just plug in some value of x and find the corresponding value of c. the easiest value that I can plug in is x is equal to 1. Right? Because if I plug in x is equal to 1, I get natural log of 1 minus natural log of a is c, and natural log of 1 is 0. So c is negative natural log of a. So if I plug that in here, I get ln x minus ln ax is negative ln a. Just rearrange everything and you get ln ax is ln a plus ln x, which is what we wanted to prove. Any questions?
Ma'am, can you please repeat from step 9 again?
Yeah, so I want to find the value of c, right? Since this is true for all x, just plug in any value of x that for which you know this expression, and that will give you c. So when I plug in x is equal to 1, this becomes ln 1 minus ln a, because instead of x, I'm plugging in 1. And c, that should be equal to c, right? Because that c satisfies this expression for all x. So ln 1 is just 0, which means that c is negative ln a. And so I plug that in, instead of c, I write negative ln a here. That gives me this. And just rearrange to get ln ax. Is that clear?
Yes, ma'am. Thank you.
Okay. So similarly, we can prove that the quotient rule, the reciprocal rule, the power rule for natural log. So the natural log converts a quotient into a difference. So ln of a over x is ln of a minus ln x. Similarly, using this expression, using the quotient rule, ln of 1 over x is negative ln x. Why? Because ln of 1 over x using the quotient rule is ln 1 minus ln x. ln 1 is 0, so this is equal to negative ln x. And lastly, the power rule says that the natural log of x raised to power some n is n times ln x. So it converts products into sums, quotients into differences, and powers into products. So this power can be brought outside ln, right? You can bring it down outside ln. So for example, ln of x squared is equal to 2 ln x. And these can all be proven just like we proved the product rule using the same technique. So the benefit of all of these properties of the natural log are that they make differentiation of products, quotients, powers easier. So if I have this function, which is, it's a product and then a quotient, we also have a power going on here. If I want you to find dy by dx, then obviously you can use the quotient rule here, but as you can see, it'll be lengthy because there's a lot of terms. So you'll have to use a combination of the quotient rule and the product rule because in the numerator, you have a product. The natural log will make this much easier. This is called logarithmic differentiation because what we do is we take the natural log of both sides of whatever equation that we want to differentiate, and then the natural log makes that expression much easier to differentiate, and then we write everything back in terms of our original function. So let me explain that through this example. The first step is that you take the natural log on both sides of this equation. What does that do? That converts, this complicated product and quotient into just a sum. How does that do that? So you have ln of x squared plus 1 times x plus 3 raised to power 1 over 2 divided by x minus 1. So this becomes ln of x squared plus 1 plus half ln x plus 3. The half comes down as, just a coefficient here. And then minus ln x minus 1, because x minus 1 was in the denominator. Now, if I differentiate, so differentiating this is much easier than differentiating this, right? So now if I differentiate both sides with respect to x, what do I get? On the left-hand side, I have ln y. So I get 1 over y dy by dx. On the right-hand side, I just have to differentiate this, which is a sum. So it's this, the derivative is the sum of their individual derivatives. So the derivative of ln x squared plus 1 becomes 2x over x squared plus 1. The derivative of ln x plus 3 becomes 1 over 2 times x plus 3. And the derivative of ln x minus 1 becomes 1 over x minus 1. Of course, we're assuming that x is greater than 1, so that this argument is positive. And now, what did we set out to find? We wanted dy by dx, right? We wanted dy by dx. We have dy by dx here. And then we have this 1 over y here. So I can take y to the other side, and I know y in terms of x. So I can write everything in terms of x. So I take y to the other side and write y in terms of x. This is my final answer. I just wrote y in terms of x using the original equation we'd been given. Any questions? Yeah, you can leave the answer here. This is fine. You don't have to simplify it further. All right, so the key thing, when you see a complicated product or a power or a complicated quotient, logarithmic differentiation helps to simplify the differentiation. One thing to remember always is that you will have this 1 over y. Students often forget to take it to the other side and often just stop here and assume that this is equal to dy by dx, which is not true. Right? You have this extra 1 over y here, so you have to take y to the other side. All right. So I've summarized the steps for logarithmic differentiation here. First step is take natural log of both sides, right? And then you get 1 over y dy by dx here, and the derivative of the natural log of f of x. The hope is that this is easier to evaluate, right? You solve for dy by dx by taking y to the other side and write everything back in terms of x. So y is f of x. So as an example, if I have x raised to power x, what is the derivative of x raised to power x? A very common mistake here is that students will write this as x times x raised to power x minus 1. Why is that wrong? The power rule is applied when you have x raised to power some number. Then d by dx of x raised to power n is n times x raised to power n minus 1. This is under the assumption that n is just a number. It is not a function of x. So n does not change as x changes. So the derivative with respect to x does not affect n. Here, on the other hand, we have x raised to power x. So you cannot apply the power rule, right? So what do you do instead? You take the logarithm. So you have y is equal to x raised to power x, right? And then you can take natural log of both sides, that is equal to x ln x. And now you can differentiate both sides. So if you differentiate both sides, you get 1 over y dy by dx, and you can differentiate this using the product rule. Right? And then I'll ask you guys to continue this on your own and find dy by dx. Similarly, try doing x raised to power sine x, right? Try finding dy by dx when y is x raised to power sine x. Again, you cannot use the power rule here because the power is a function of x itself. So when you take the derivative, you have to account for how much the power changes when x changes. All right? So try doing both of these on your own. I've almost done pretty much half of x raised to power x here, but try doing both of these on your own by following these steps of logarithmic differentiation. Any questions? All right. So in the beginning, I said that the integral of 1 over x dx is ln x plus c when x is greater than 0. And I said I'll deal with what happens when x is less than 0 in a bit. So now we're going to deal with that. What if x is less than 0? I cannot write this because I cannot have natural log of a negative number. Natural log is defined only for positive numbers. So now let's consider integral of 1 over x dx. X is less than 0. What can I do? I can use a substitution where u is equal to negative x. So if x is negative, u is positive, right? And so du by dx is negative dx. So I can rewrite 1 over x dx as 1 over negative x negative dx. And so 1 over negative x becomes 1 over u, and negative dx becomes du. And I get ln of u plus c, right? So this, I know u is positive. So I know that the integral of 1 over u du when u is positive is ln u plus c. And if I write everything back in terms of x, it's ln of negative x plus c. So the integral of 1 over x dx is ln x when x is positive and ln of negative x when x is negative. Is there a concise way to write this? You have ln of x when x is positive, but you have ln of negative x when x is negative. Is there a concise way to write this? Yes, using the absolute value. This is just ln of absolute value of x plus c, of course, right? So the integral of 1 over x dx is just ln of absolute value of x plus c. Now you don't have to worry about whether x is positive or negative. This accounts for both those cases. Yes, Amna?
Ma'am, can you please repeat the substitution part that you did? I couldn't understand it.
Okay. So the reason I did that substitution was so that inside this integral, I have 1 over something positive. X is negative, so I wrote u is equal to negative x, which makes u positive because x is negative, right? And so du is just negative dx. Now, instead of 1 over x dx, all I did was multiply and divide by negative 1. So I have negative dx over negative x. Just multiply and divide by negative 1. It doesn't change my original expression. Negative dx becomes du, and 1 over negative x becomes 1 over u. Now, by doing this manipulation, what you can do is you can now evaluate this integral because it's integral of 1 over a variable that is always positive with respect to that variable. Right? So this becomes ln u plus c, and then you get ln of negative x plus c when you write everything back in terms of x. And so if you want to write it in a concise way without separating the two cases, you get integral of 1 over x is ln of absolute value of x plus c. So now we're able to integrate 1 over x dx, which we couldn't do based on the power rule earlier. We couldn't use the power rule when n was equal to -1. All right. So now that we know, the integral of 1 over x dx, we are now ready to evaluate the integral of tan x, which we haven't done so far, right? So we know the integral of sine, we know the integral of cos, we don't know the integral of tan. Tan can be written as sine over cos, right? And so now if I do a substitution here, where u is equal to cos x, then du is negative sine x dx, right? So this becomes, if I just multiply and divide, this becomes negative sine x dx, and then another negative here over cos x. So negative sine x dx becomes du, and cos x is u. So you get negative du over u. So basically the integral of negative 1 over u du. And that we know is just negative ln absolute value of u plus c. And u was cos x, so we write everything back in terms of x. So it's negative ln absolute value of cos x plus c. You can stop here if you like, or you can write it in a more concise way by using the property of logarithm. So this negative becomes ln of absolute value of cos x raised to power -1 plus c. And so that's ln of 1 over absolute value of cos x plus c. And that's the same as ln of absolute value of secant x plus c. Any questions? How did sin x become negative du? Sin x did not become, sin x dx is negative du, right? Look at this here. U is cos x, so du is negative sin x dx. So sin x dx is negative du. Right. So similarly, you can show, using the same approach, you can show that the integral of cotan x is negative ln absolute value of cosecant x plus c. Don't forget these absolute value signs, all right? Because secant and cosecant can both be negative, and you want to make sure that the argument of the natural log is positive. All right. So we're just going to do a little bit of exponential because I want you guys to at least be introduced to it, and we're just going to do the integral and derivative of it, and that's pretty much it. So we just have 3 more pages. I think we might have to go 5-10 minutes above time, but we're going to end it at the end of this lecture set because you have to use exponentials in later courses, and I don't want you guys to miss out on that. So the natural log of x is a 1-to-1 and onto function, right? If you just remember the graph, this was the graph. It's 1-to-1, right? Why is it 1-to-1? Because it passes the horizontal line test, right? And it's onto the entire set of real numbers, meaning it can attain all real numbers, right? Its range is R. So it has an inverse. Let me call that inverse ln inverse of x. It must have a well-defined inverse. Let's call it ln inverse of x. Now I'm going to define a number such that, so I'm going to call that number e, and I'm going to define it such that ln inverse of 1 is equal to e. So I'm going to choose, basically I have to find that number such that ln inverse of 1 is equal to e, or equivalently ln of e is equal to 1. meaning I have to find that number. Remember, ln was the area under the curve of 1 over t from 1 to x. So I have to find that number e such that the area under this curve is exactly equal to 1. E is that number. If you evaluate E, it is an irrational number. If you try to find that E using a computer or a solver, E is an irrational number, which the first few decimals are 2.71828. So it's a number between 2 and 3. It's an irrational number. All right, so E is that number that makes this area equal to 1. Now, notice that the natural log of e raised to power x, which is just x times ln e, is x. Because ln e is equal to 1. We defined e to be the number such that ln e is equal to 1. Right? So ln of e raised to power x, using the properties of logarithm, become x times ln e. Ln e is equal to 1, and so this is just x. So that means that ln of e raised to power x is x. Now, if I take ln inverse of both sides, remember ln inverse is a well-defined function. If I take ln inverse of both sides, what do I get? I get e raised to power x is equal to ln inverse of x. And I just took ln inverse of both sides of this equation. So now e raised to power x is ln inverse of x. Instead of ln x, if I write e raised to power ln x, then that's ln inverse of ln x. And so e raised to power ln x is equal to x. The point of all of this is to show you that if I have the composition of ln x and e raised to power x in any order, so if I have ln of e raised to power x, that's equal to x. If I have e raised to power ln of x, that's equal to x. What does that mean? So I'm composing two functions, and when I compose them in either order, I get the same input back. That means that e raised to power x is the inverse of ln. So the inverse function that we were looking for is equal to e raised to power x. E is a number, it's a fixed number, it's a constant. X is a variable. Right? X is the variable of the function. So the inverse of ln x is e raised to power x. Any questions? All right, so since this is just e raised to power x, the laws of this exponential function work similar to how we work with usual powers. So e raised to power x1 times e raised to power x2 is just e raised to power x1 plus x2, right? Just like 2 raised to power 2 times 2 raised to power 3 is 2 raised to power 2 plus 3, right? So the laws of the exponential function are similar to the usual exponents that we've seen. To show that that's actually true, based on the definition of the exponential function, let's try and prove it. If I let y1 be equal to e raised to power x1 and y2 be equal to e raised to power x2, right? Then x1 is ln y1 and x2 is ln y2. Just by definition of the exponential function, right? The exponential function is the inverse of the natural log function. So x1 plus x2, using this, x1 plus x2 is ln y1 plus ln y2. And using the properties of logarithm, that's ln y1 times y2. So x1 plus x2 is ln y1 plus, ln of y1 times y2. Let me just write that here. X1 plus x2 is ln y1, y2. So that means y1, y2 is e raised to power x1 plus x2. Just take exponential of both sides. And so if y1, y2 is e raised to power x1 plus x2, that means that e raised to power x1 times e raised to power x2 is e raised to power x1 plus x2. Because y1 was e to the power x1, y2 was e to the power x2. So all we're really doing is using the properties of logarithms to find corresponding properties for exponentials. Any questions? And so similarly, you can prove that e raised to power negative x is 1 over e raised to power x. E raised to power x1 over e raised to power x2 is e to the x1 minus x2. And e to the x1 whole raised to power x2 is e to the x1 times x2, which is the same as e to the x2 whole raised to power x1. Right, so these laws of exponents should hopefully be familiar. Not if you've done the exponential before, then definitely, but even if you haven't, these are similar to the basic laws of powers that we have for numbers. All right, so just a reminder, natural log of 1 is 0, and so the exponential of 0, or e to the 0, is equal to 1. ln of 1 is 0, so e to the 0 is equal to 1. Which is in line, so any number, any non-zero number raised to power 0 is equal to 1, right? Where a is not equal to 0. And since e is just a number, this makes sense. Sorry, yes, Rafi, this is the last law here. Okay. All right, so any questions before we derive the derivative of e to the x? All right, so the derivative of e to the x is actually one of the easier derivatives that you would have seen. Y is equal to e raised to power x, right? So I want to differentiate this. X is in the power, right? So let's use logarithmic differentiation to get dy by dx. So I take natural log of both sides. So ln y is equal to x, and differentiate both sides now. So that means 1 over y dy by dx is equal to 1. Just differentiate both sides with respect to x. Now take y to the other side. We're doing the usual logarithmic differentiation that we just learned. If I take y to the other side, that means dy by dx is equal to y. So we get e to the power x again. So the derivative of e to the x is just e to the x again. It's one of those functions that when you differentiate, you get the same function back. Right? So the slopes of the tangent line of this function are the function itself. So again, you can, now that you know the derivative of e to the x, you can combine the exponential function with other functions and then use all the properties of differentiation that you've done so far. So the derivative of e to the f of x, if I differentiate this, that's just e to the f of x times f prime of x. This is just using the chain rule. Also, since the derivative of e to the x is just e to the x, then the integral of e to the u du is e to the u plus c. And you can even use x, so e to the x dx is e to the x plus c. Any questions? All right, so let's just do some examples on this last page and then we're done. All right, so I want to evaluate the integral of e to the 3x from 0 to ln 2. All right. So, I mean, you can do this by just doing the substitution, subconsciously. But if you want to write it out, you can use the substitution u is equal to 3x. And so du will be equal to 3dx. So you multiply and divide by 3, right? And so 3dx becomes du. This 1/3 you can take outside, and e to the 3x becomes e to the u. Now, what's the one last thing that you need to do? You also need to adjust the limits of integration. So when x is equal to 0, u is equal to 0. When x is equal to ln 2, u is equal to 3 times ln 2, which you can also write as ln 8, because this becomes ln 2 raised to power 3, is ln 8. So now the integral becomes this, 1/3 times the integral of e to the u du from 0 to ln 8. Right? And what's the integral of e to the u du? That's just e to the u again, right? And so remember, you still have to apply the limits of integration, so don't forget to keep a track of them here. From 0 to ln 8, so it becomes 1/3 times e to the power ln 8 minus e to the power 0. What's e to the power ln 8? Remember, exponential function and logarithmic function are inverses of one another. So e to the ln x is just x. So e to the ln 8 is just 8, and e to the 0 is 1. So you get 7/3. All right. Any questions? All right. And so looking at, the fact that the natural log and the exponential function are differentiable wherever defined, they're also continuous. You can also see that from their graphs. So this was the graph of the natural log function. Let me actually draw a better graph. 1 second. So this is the graph of, first let me draw the y is equal to x line. And so this pink graph is, actually 1 second. Sorry, 1 second. All right, so the graph of the natural log of x looks like this, right? Where at 1 you have an x-intercept. So the graph of the exponential function looks like this, where at 1 you have a y-intercept. Right, so this is the graph of e to the x. And you can see that wherever they are defined, we can draw the graph without lifting our pen, so they are continuous throughout their domain. Both of these functions, the exponential function and the logarithmic function, are differentiable and continuous throughout their domains. The domain of the natural log function is just all strictly positive real numbers. The domain of the exponential function is all real numbers. Any questions? All right. So we can stop here. So that's the end of the course. If we were in a regular semester, we would have done a few more topics. If you want, I can upload notes for those. I mean, they won't be part of our course, but for those of you who are interested, if you want, I can upload notes for those topics. They include integration by parts, trigonometric substitution, and so on. So I can upload notes for those if you like, and you can maybe try and study them on your own. And if you have any questions, I'd be happy to answer. But how long will the final be? I think 2 hours or 2.5 at the most. So I haven't planned it out yet, but 2 to 2.5 hours. Right, so do you guys want me to upload the notes of the extra topics to LMS? even though they won't be part of your syllabus? All right, so I'll upload those. I think there's just 2 more lecture sets. And again, if you have questions on those or anything in the course, I'd be happy to help. This is the end of our lectures, but I'm going to be holding extra office hours. So my usual office hours as well as extra office hours before your final. So if you have any questions, please feel free to email me or come to my office hours, all right? Other than that, thank you all for joining, and thank you all for consistently attending classes. I know that this has again been a continuation of this online situation that seems to keep getting worse and worse, but hopefully I hope that next fall we can all come to campus and see each other and live a more normal life. But in the meantime, please take care of yourselves and of your families. The situation is getting worse again. So inshallah, hopefully, we can all stay down until this becomes better and come out of it healthy and safe with our families and friends, inshallah. So best of luck for your finals. And again, let me know if you have any questions at all. I'm always here to help, all right? Thank you all. Take care and good luck with everything. Khuda Hafiz.